All right, so let's take a look at the CUDA array multiply example. This has also been shown in the CUDA notes. I try and make my note sets somewhat complete, standalone note sets. And so I'm repeating it here. And I'm going to do the same live example I did in the CUDA notes. So you can skip over one or the other or hear it again. Who knows, maybe it'll turn out differently this time. Okay, so this is what the CUDA code looks like. It's in a .cu file. It has both the CPU and the GPU code in the same file. This is a pound include you need, and it's got some things that the CUDA runtime needs. These are some helpful .h's, and I'll give you these. Here we're setting up threads per block. We've got it set up so we can set it from the compiler line, or we can just default it. Same thing with data set size. So we're defaulting threads per block to 128, and we're defaulting the data set size to 8 million floating point numbers. First time I did this, when I set up data set size, I called it array size. That seemed to me to be the obvious thing to do. It turns out array size is already used in one of CUDA's .h files. It took me a long time to figure out what that error message meant. Because if you say pound define array size, it takes whatever it's been defined to before and puts that in there, which is a complete syntax mistake. Anyway, don't use the phrase array size in a CUDA program. So here are the host arrays, A, B, and C. I begin them with lowercase h to make sure everyone knows they're host arrays. This is an error checking function. CUDA doesn't actually throw errors that you can see. It sets a flag internally, and you have to run out and check it. So that's what this CUDA get last error function is. It's running out and checking the flag, returning something, and if it wasn't a successful thing, it will print something to let you know, what line was it in when something went wrong. All right, here's the kernel function, underbar, underbar global, underbar, underbar. That flags it as the kernel function, callable from the CPU, but executes on the GPU. We're going to be passing in 3 arrays. Here's our global identifier using these built-in variables. And this is just a safety thing. If it comes out to an even number of blocks, everything's fine. But if it spills over into a partially filled block, this makes sure you don't start using memory you don't actually own. Here we're setting up the host arrays. Here we're allocating dynamic memory over on the GPU. This is what will get filled with the address, probably not the real address, probably more like a index in a memory address table. We don't care really. And then this is how many bytes to allocate over on the GPU. So A, B, and C have been allocated. We're now copying. The CUDA memcopy function always takes a second argument, copies to the first. Second argument copies to the first. So the host version of A gets copied to the device version of A. Host B to device B. Again, throw in a little check error, why not? We don't have to copy C over because it's going to be coming back. Here we're setting up the execution parameters. This grid, which is really an integer 3-element array, is the number of blocks. So if I know the threads per block I wanted, and I know the size of the problem I'm trying to solve, that tells me how many blocks I want. So here's the number of blocks. Here's the number of threads per block. That's what we'll use when we call the kernel function. This just makes sure the GPU has gone quiet. That is, don't start timing anything if the GPU is too busy doing something. This sets up times that we're going to use to click the stopwatch. And here we're clicking the stopwatch. Okay, click. Ready, go. Here we're calling the kernel. We're calling the name of the function with arguments, just like we would do in C, only we've inserted this chevron stuff in here. Number of blocks, number of threads per block. You get to set that. GPU goes, okay, here's what they want. Let's go set it up. It turns out this function call returns immediately. That's just how this works. Because for all it knows, you have other things you want your program to go off and do. Well, at this point, we don't. We want to wait till it finishes, and that's where we use this function call again, CUDA device synchronize. It just blocks until the GPU has gone quiet, until the GPU is no longer doing anything. So here we are clicking the stopwatch to stop at the end of the program. That is, we have called CUDA device synchronize. It's now come back. That means the kernel function is done running. We're going to click the stopwatch. It's going to return to us a number of milliseconds between the start and stop. We're going to turn that into seconds. We're going to take seconds and turn it into multiplies per second, and that's going to be a big number. So we're going to divide by 1,000,000 so that we can call it mega multiplies per second, and we're going to print it out. And if we wanted the results back, and here we're doing timing, but if we actually were doing useful work and we wanted the results back, we would do another mem copy. Again, second argument goes to first argument. And here's how you clean everything up. All right, this is what the make file looks like. You know, actually, instead of talking about that, I think it's time to go run it. So we will, yeah, all right, here we go. So there's ArrayMult.cu. There is no ArrayMult.cpp or .c in here. It's all .cu. We are over on a Linux machine that has a GPU. If I look at the make file, sure, there we go. If you wanted to use version 11, uncomment this or uncomment this for 12. But there's nothing in CUDA 11 or 12 that we need for this class. So CUDA 10 is fine. And that guarantees it runs anywhere you can find a GPU at Oregon State. Okay, and here's what we're going to do. If we want ArrayMul, we need ArrayMul.cu. And if we've got it, here's what we do to compile it. So if I just say make, boop, there we go. And if I say ArrayMul, there we go. 8 mega data values, 128 threads per block, 14,407 mega multiplies. Wow, that's 14 giga multiplies per second. 14 billion numbers got multiplied in the time it takes you to say 1001. Not too shabby. Now, this is what GPUs do. Let's put this in a loop. So if I do that, there we go. And I only put in one for loop. I'm just looping through threads per block. We can loop through data set sizes in a second for loop, just like we've done before. Here's the compiler. Here we're doing the -D trick, and we're outputting it. And so let's run that. Eight, 32, 64, 128. All right, so let's take a look. So 8 threads per block is really wasting 3/4 of the threads that the block is capable of having. So our performance is low, although this is 2 billion to almost 3 billion multiplies per second. So it's hard to describe that as horrible performance, but in the GPU sense, it is. If we go up to 32, then we get almost 9 billion multiplies per second. That makes sense. If we go up to 64, we get almost 13 billion multiplies per second. So you can see there is an advantage in having more than one set of 32 threads in at a time, because sometime that first set of 32 is going to have to stop, on a memory fetch, say, and then we have another set of 32 that can come in and keep running. Now you can see that after, 128 is a little bigger, and after 128, it really isn't any bigger. So the curve has flattened out. Basically at 128, we've saturated what that part of the GPU can do. There is no more idle time to try and sop up. But anyway, there you go. Little piece of code gets you 16 billion numbers per second multiplied. I just have a hard time sort of understanding arithmetic at that magnitude, but it's kind of cool.